All right, welcome back. Let's do some examples of optimizing on a closed interval. So here's the problem. Optimize function f equal to 2x cubed minus 15x squared plus 24x plus 7 on the interval 0 to 6. Okay? So I have to find all the critical points first. So the critical points here will just be where the derivative is non-zero, so that means I have to solve, that's where the derivative is 0. Solve f prime of x equals to 0, which means I need the derivative. So f prime will be 6x squared minus 30x plus 24. I guess we can factor a 6 out. So x squared minus 5x and a plus 8. That's not true. 6 times 4 is 24. All right, let's factor that. So we get an x, about a minus 1 and a minus 4. All right, so the critical points will be x equals to 1 and x equals to 4. And now we have to make a table with the endpoints and the critical points. And plug them into f. All right, so here will be our table. We'll put critical points or endpoints. And remember, our function was 2x cubed minus 15x squared plus 24x plus 7. All right, so the critical points were 1 and 4, and the endpoints were 0 and 6, and so we have to plug everything in here. All right, so that's a little unpleasant, but I already calculated these. So at 1, we got 18. At 4, minus 9. At 0, of course, 7. And at 6, you get 43. And from this, you can see this is the global minimum, and this is the global maximum. So if they ask what is the maximum, the answer is 43. If they ask where the maximum occurs, the answer is it occurs at 6. Same thing for minimum. The global minimum is negative 9, and it happens at x equals to 4. Okay? All right, let's do another example. All right, here, let's do the following. Optimize the function f equals 1 minus x minus 1 to the 2/3 on the interval minus 1 to 2. All right, so we need critical points. That means we have to calculate the derivative. So the derivative will be minus 2/3 times x minus 1 to the minus 1/3. So that's minus 2/3 times 1 over, the cube root of x minus 1. All right, this is never 0 because it's a 0 if you can make the numerator 0, and it'll blow up if you can make the denominator 0. However, as you can see, the denominator can try to become 0, which makes the derivative undefined. But f prime, so f prime does not exist at x equals to 1 because we get, or try to get division by 0. So that's our only critical point. All right, step 2 is to make this table. So here we go. We put either the critical points or the endpoints, and you put your function here. And that was something like 1 minus x minus 1 to the 2/3. Oh, by the way, remember the interval we cared about was -1 to 2. So 1 is in there, so we definitely want to keep it. If the critical point weren't in there, we wouldn't include it on the table. All right, so the critical point was 1, and the endpoints were -1 and 2, so we have to plug everything in here. All right, so for 1, you can evaluate that exactly. You get 1, and the rest give you, well, you can put it on, they'll give you cube roots of things, so you can put it on your calculator to get an approximation. And so f of -1, let's see, f of -1 is approximately -0.59, so you can put that on your calculator. And then f of 2 is 0. All right, so from this we see that we have a global maximum here, and the value is 1, and we have a global minimum here, and that happens at x equals to -1. That's it for optimizing on a closed interval. Have fun!